Like clockwork, every 22 minutes for the past 35 years, a mysterious signal has pierced the silence of space and made its way to Earth. This signal, known as GPM J1 1839-1842, isn't from a satellite or any man-made object. It originates from the depths of space, and it has captivated scientists around the globe. What could be the source of this signal, and why should we pay attention? Today we'll dive into a cosmic mystery that challenges our very understanding of the universe. Let's begin. So how can we unlock the secrets of such a signal? The answer lies in radio astronomy, the field that has made space exploration possible. The story of radio astronomy began in the 1930s when American physicist Carl Jansky was investigating radio interference. During his research, he made an unexpected discovery: radio waves coming from the Milky Way. This accidental find marked the birth of radio astronomy. Unlike traditional astronomy, which focuses on visible light, radio astronomy listens to the universe by tuning into frequencies invisible to the human eye, revealing celestial phenomena that would otherwise remain hidden. Since its inception, radio astronomy has undergone a technological revolution. Today's radio telescopes are engineering marvels, capable of detecting signals from unimaginable distances. In the remote outback of Western Australia sits a unique space detective, the Murchison Wide Field Array. This isn't just any telescope. It's a sophisticated network designed to probe the furthest corners of the universe. Composed of thousands of antennas spread across an arid landscape, the Murchison Wide Field Array is a testament to human curiosity and ingenuity. Each antenna functions like a finely tuned ear, listening intently to the faintest whispers from space. Behind the scenes, a team of dedicated scientists and engineers work tirelessly to calibrate and maintain this intricate system. Their mission? To capture signals across a broad range of frequencies, a crucial task for studying different celestial phenomena, each with its own unique radio signature. Once captured, these signals are processed in a cutting-edge data center where powerful algorithms sift through the cosmic noise, identifying patterns and anomalies, turning raw data into valuable scientific discoveries. Among the array's most fascinating finds are fast radio bursts, or FRBs. These high-energy phenomena are incredibly brief, lasting only milliseconds, yet they emit as much energy as the sun does in nearly a century. It was within this cosmic cacophony that our mysterious GPM J1 1839-1842 signal was discovered. Unlike other signals, this one has a rhythmic pattern and has been consistently reaching Earth every 22 minutes for the past 35 years. What makes this signal stand out is its consistency and longevity. While most cosmic signals are random or short-lived, this one has proven to be both stable and constant, making it a subject of intense study and debate. So what makes GPM J1 1839-1842 so unique? Its 22-minute periodicity acts like a metronome in the vast orchestra of cosmic signals, a rhythmic constant in a sea of variables. Further analysis reveals even more peculiarities. The waveform doesn't follow the typical profiles of known celestial radio emissions. Its frequency and amplitude exhibit nuances that have yet to be fully understood, complicating an already baffling mystery. Many theories have been proposed, ranging from rotating neutron stars to highly magnetic magnetars, and even more exotic ideas like interactions between double black holes. However, none of these theories completely fits the data, leaving the scientific community in a state of intrigued bewilderment. When it comes to unexplained radio signals from space, suspicion often falls on pulsars, celestial beacons known for emitting beams of radio waves, making them prime suspects for any mysterious cosmic chatter. But what exactly are pulsars? Pulsars are neutron stars, born from the remnants of massive stars that have gone supernova. They spin at incredible speeds, and as they do, their magnetic fields generate beams of electromagnetic radiation, including radio waves. These waves sweep across space like lighthouse beams across the sea. When these waves cross Earth's path, our radio telescopes pick them up as pulses, hence the name pulsars. Pulsar signals are usually very regular, often with millisecond accuracy, which has even led to their use as cosmic clocks to aid in tasks like spacecraft navigation. So, could GPM J1 1839-1842 be a pulsar? At first glance, it might seem likely given its rhythmic 22-minute interval. However, upon closer examination, the differences become clear. Unlike typical pulsar signals, which have a consistent shape and amplitude, GPM J1 1839-1842 exhibits characteristics that set it apart. Its waveform doesn't match the profiles we usually associate with pulsars, and its amplitude shows variations that remain unexplained. Moreover, the signal's longevity and unchanging nature contradict what we know about pulsars, which can slow down over time as they lose rotational energy, affecting the timing of the signals they emit. Despite the similarities, GPM J1 1839-1842 appears to be something entirely different. While pulsars are often the first suspects when it comes to mysterious radio signals, magnetars are not far behind. Magnetars are neutron stars with magnetic fields so intense they defy comprehension. To grasp the magnitude of a magnetar's magnetic field, consider this. It is about 2 quadrillion times stronger than Earth's magnetic field, and 20 trillion times more powerful than a refrigerator magnet. These magnetic fields are so strong, they could erase data from a credit card halfway to the sun. Magnetars are known for their bizarre properties. They emit X-rays and gamma rays but can also produce radio emissions, often associated with stellar earthquakes, seismic events on the surface of a magnetar that release enormous amounts of energy. Imagine an earthquake but on a cosmic scale. These stellar quakes can distort the magnetar's magnetic field, causing the release of energy in the form of electromagnetic radiation, including radio waves. So, could a magnetar be the source of our mysterious GPM J1 1839-1842 signal? At first glance, it might seem possible, given magnetars' strange behavior. However, the concept of a stellar quake doesn't fully explain the consistent 22-minute interval of the signal, nor its longevity. Stellar quakes are sporadic events, and their emissions wouldn't have the rhythmic, clock-like precision of GPM J1 1839-1842. While magnetars offer an intriguing possibility, the lack of supporting evidence sends us back to the drawing board in search of a better explanation. As we continue to explore astrophysics theories regarding GPM J1 1839-1842, white dwarfs come into the picture. These are the remnants of stars that have exhausted their nuclear fuel. They are incredibly dense, have strong magnetic fields, and could theoretically cause radio emissions. However, while their magnetic fields are strong, they don't exactly match the features observed in GPM J1 1839-1842. Another frontier theory leads us to the dynamic interactions between stars and exoplanets orbiting them. In this cosmic dance, the magnetic fields of the star and its exoplanets could interact in ways that produce unique radio emissions. While this theory offers a fascinating avenue of investigation, it also comes with its own challenges. Such interactions would likely produce a wide range of signals rather than the steady 22-minute cycle we observe with GPM J1 1839-1842. While this theory breaks new ground, it's not entirely consistent with the data we have. Magnetic interactions between double brown dwarfs are another possibility, but they would likely produce a more chaotic signal rather than the rhythmic, clock-like pulse of GPM J1 1839-1842. A new perspective is emerging that takes into account the environment in which the signal exists. Could surrounding cosmic debris and stellar winds be influencing the signal patterns we observe? Imagine a radio signal traveling through space and encountering asteroids, gas clouds, and streams of charged particles along the way. These environmental factors could act as space filters, altering the characteristics of the signal by the time it reaches Earth. This idea isn't purely speculative. Studies have shown that space debris can indeed affect the properties of radio signals, causing changes in amplitude and even frequency. But is this the case with GPM J1 1839-1842? Interestingly, the results of fast radio burst 28-0916b offer some parallels. This particular FRB exhibited patterns that were puzzling at first, but were later found to be influenced by the local environment, including the presence of a nearby magnetar and surrounding cosmic plasma. Could a similar environmental influence be at play with GPM J1 1839-1842? Although the contexts are different, The idea that local space conditions could affect a radio signal adds another layer of complexity to our understanding. As we approach the final frontier of this study, it's time to consider the broader implications of this enigmatic signal and what the future holds for its investigation. Fortunately, the source of GPM J1 1839-1842 continues to intrigue scientists who are planning to carry on with their observations as well as examine archival images in search of similar phenomena in the Milky Way. Their ongoing efforts aim to solve this mystery, and their initial results are promising. The discovery of GPM J1 1839-1842 has confirmed that ultra-long-period radio sources are not as rare as previously thought.